In this video, I'm going to go over all the questions that I posted for the final exam review. So I'm going to talk about all the solutions, and I suggest you go over the question first and then take a look at the solutions. Okay, now let's start with the first question. The first question is about to determine the size of the matrix product. Okay, so here I give you two matrices. One is A. So A is n by n matrix, and B is n by p matrix. Okay, so the question is, what is the size of A times B? Okay, the matrix product. Okay, the size of A times B is basically determined by this. So n by n, this is B is n by p. Okay, so in order to compute the matrix product, so the second number here and the first number here, they must be equal. And in particular, the product will be just AB, the size of this product. Let's do this one. The size of this guy is determined by this guy and this guy. So it's n times p. So that's the size for the matrix A times B is n times p. Okay. And the second question, okay, along with the first question, there's an example showing that the question example is A is, okay, A times B is, so I give A is 1, 2, 3, and 3, 2, 1, and B is 3, 2, 1, 2, 1, 3, and 1, 2, and 3. So the first matrix is 2 by 3, so is 2 row, is number. So the size of A matrix is number of row times the number of column. So I have row 1, row 2, column 1, column 2, column 3. So it has 2 by 3, right? And this guy is 3 row and 3 columns, so 3 by 3. So by computing the product will be just, you ignore the second number over here, you ignore the first number for the second one. So you have the size of A times B is 2 by 3. We know the size 2 by 3, okay? So the product given by is computed in this way. So it is so it's 2 by 3, okay, so which means it has sort of this 2 rows and 3 columns. The first one is given by this first row times second column, which means we do entropy product and we compute the sum. So this guy will be just 1 times 3 plus, so it's 2 by 2 plus 3 times 1, okay? So the second number here is given by first row times the second column. So we do entry as a product and we compute this, and then compute the sum. Is 1 times 2 plus 2 times 1. This is 2 times 1 plus 3 times 2. Okay. So you follow the same rule. So the third one will be this first row times third row, and so on and so forth. So if you follow the rule, the final product, the value will be 10, 10. 16, 14, 10, and 12. So that's it's 2 by 3 matrix. Okay. So that's the first question. Second question is, let 2 be an eigenvalue of A with associated eigenvector 2, 1, 1, 2, 3. So for A, I know, hey, it has an eigenvalue of A. I know one of them is 2, and eigenvector for this eigenvalue associated with matrix A is 1, 2, and 3. So the question is, what is eigenvalue of A squared? Okay, can we say eigenvalue of A squared? Okay, and also the associated eigenvector is what? So that's the question. Okay, so according to the definition of eigenvector, if A2 is the eigenvalue of A with the associated eigenvector of this guy, we have A times 1, 2, 3 is equal to 2 times 1, 2, 3. That's the definition of the eigenvector. So if I take this one, so I do A squared times 1, 2, 3, which is equal to A times A times A, 1, 2, 3, right? So we keep this one, we do this one. This guy will be equal to, according to the first one, we keep this a to be here. Okay, so a, this guy times this guy will be the 2 times 1, 2, 3, right? So I can keep the 2, move 2 to the front. So it's 2 times a times 1, 2, 3. Now we use this one again, so it's 2 times 2 times 1, 2, 3, which means equal to 4 times 1, 2, 3. Okay, if you compare this one, so this guy, so a squared times this guy is equal to 4 times the same thing, according to the definition of an eigenvalue, eigenvector. So a squared has eigenvalue of this value, which is 4. Eigenvector will be, yeah, it's still the same eigenvector. Okay. That's the second question. Okay, third question is about vector operations. So go to the third question, vector operations. So the third question is about a dot and cross product of 2 vectors. So give 2 vector a1. A is 1, 2, and 3. B vector is 2, 1, and 3. Okay. And so the question is to compute A dot B, A cross B, and B cross A. Okay. Okay, so now first let's start with this dot product. So A dot B is, you do entry-wise product of the 2 vectors, which means you do the product first entry of the A vector and the first entry of B vector. Then you compute the, essentially do is you do the product of this first one times the first one, then you do the second one times the second one, second one times second one, and you do the third one times third. You do the product. You basically do all the product. After you do the product, you have 1 times 2 plus 2 times 1 plus 3 times 3. You do the sum. That's the dot product. Okay. So which is, this is a 2 plus 2 is 4. 4 plus 9 is 13. That's the dot product. Cross product is, so cross product only applies to a 3D dimensional vector. You cannot have 4-dimensional vector. So the computation is given by this. You do have I, J, and K. Then is by computing a 3x3 made a determinant of 3x3 matrix, and the first row is ijk, and the second row is whatever a vector you have, the first vector in the product. So it's 1, 2, 3, and then you put b as the last row. Is 2, 1, 3. Okay. So I will not go to the detail of the. So this is determinant. You basically can calculate this as, if you use the first row to compute the determinant, is I times -1, 1 plus 1. The first row, first column have 2, 3, and 1, and 3, plus j times -1, 1 plus 2. So this is 1 and 1 is the first row, first column. This is 1 plus 2 is first row, second column. So it is 1, 3, 2, 3, plus k, -1. This is 1 plus 3 is first row, third column. And then you delete the first, the rows and columns, this k is on. So you do the first row and last column, you have 1, 2, 2, and 1. So the 2 by 2 matrix, the determinant will be just 2 is the product of the diagonal entries minus the product of diagonal entries. So this one, I just do a computation directly. So the product will be just I times 3 plus j times 3 is the final j times 3. You do the product plus k times minus 3, basically. Okay, so which means this is, you also write this as vector, is 3, 3, -3. Okay. Now the last one is b cross a. Okay, you can directly use the property b cross a is just -a cross b. Okay, of course you can still use the definition over here to compute the determinant of a 3 by 3 matrix, but the easiest way to compute this one is just -a cross b, which means it's -3, -3, 3. Okay. Okay, let's go to question number 4. Okay, so I'm still talking about vector operations. So we're given 2 vectors a and b, 2 vectors. and the length of the first vector is 2. The length of the second vector is 4. Okay, so if the question is if a dot b is equal to 0, so what is the smallest angle between the two vectors? So what's the smallest angle between A and B? Okay, so now we use the physical. The previous one we use the definition directly. What is the dot product? What is cross product? So this one we talks about some physical meaning of the cross product and dot product. So dot product can also be written as A dot B is equal to the A magnitude, which is the length of A times B, the length of B times cosine gamma. So gamma here is the angle between A and B. Okay, so if you use this one, so because A times B, A cross dot B is 0, and this guy is 2 times 4 cosine gamma, which means I have cosine gamma is equal to 0, because if you divide 8 on both sides, divide on both sides, so you have cosine gamma is 0. So cosine gamma is 0 because the minimum angle is pi over 2, right? Because cosine of pi over 2 is 0. That's the smallest angle. Okay, so this is the problem, the fourth problem. Okay, let's go to the question number 5. It's still vector operations. So the fifth question says, if I still give you two vectors A and B, and A magnitude is again 2 and B magnitude is 4, and if A dot P is 0, 0, 0. Okay, so my question is still, what is the smallest value? What is the smallest angle? Smallest angle between A and B. Okay. All right. So here we also use the property of the physical meaning. So as we know, if I have A cross B is equal to 0, 0, 0, what's going to happen is I can say, hey, A cross B, the magnitude is 0, right? Because the magnitude of a matrix is given by square root of the number squared, 0 squared plus 0 squared plus 0 squared, right? Which is 0. Now this one, this guy we can also have, because the property says norm of A cross B is A dot B times sine gamma. So the gamma is angle between A and B. Okay, so now because this one we calculate, this one is 0, right? This A is 2, norm magnitude, and B magnitude is 4 times sine gamma. So here is the sine gamma. So which means sine gamma is 0, right? Sine gamma is the smallest gamma is just 0, right? Okay. Okay, this is question number 5. Okay, question number 6. Next couple questions about the gradient divergence and the curve for the vector field. Okay. Question number 6. So it says if I give this f, x, y, and z, which is equal to 3x squared plus 3y squared plus z, and the question is compute the gradient of this f, x, y, z. So basically I give you the f, x, y, z, which is a vector field, okay, which means for every point you can define in the field, you can define a vector. So okay, the gradient is also notation as this: gradient of f, x, y, and z is given by partial f, x, y, and z over partial x times I plus partial f, x, y, and z over partial y, j. This is I vector, j vector, and partial f partial z times k vector. Okay, that's so what basically says gradient will return direction for a vector, a scalar field. Okay, so which one is given by partial fxy? So this fxyz is given by 3x squared plus 3xy squared plus z. So partial f over partial x, you just consider y and z be a constant. Okay, and so this partial derivative, just take a derivative of each component with respect to x. Okay, so partial 3x squared over partial x will be 6x, and partial 3y squared, because y is not a function of x, so it's 0. Partial z also partial, because z is not a function of x, so it's also 0, which means this is 6x. Plus, so partial fxy over partial y do the same thing. Partial 3x squared, the first component, partial x 3x squared, partial y is 0 because x squared is not a function of y. Partial 3y squared is 6y. Okay, partial z over partial y is also 0, so which means 6y times j. Partial f over partial z, so here let's see x, y, and z. Okay, so because you do the same thing, partial x squared over partial z is 0, partial 3xy squared over partial z is also 0, partial z over partial z is 1, so it's a 1. Okay, so that's the gradient of this scalar field. Okay. Question number 7. If I give you vector field, okay, v x y z, which is zi plus xj plus yk, I want to compute the divergence and the curl. So question, compute divergence. What this is div of v vector and curl curlf, oh not f, v. Okay. Okay, so here's what's the definition of divergence. So divergence of this v vector is given by partial, the first one, whatever in front of I over x, and whatever partial, the second over j, whatever function in front of j over y, plus whatever in front of y, k over z. So that's my divergence. Okay, you do the sum. Okay, you do the partial derivative and compute the sum. Partial z apparently 0, partial x will apply as 0, and provided 0, so this is 0. Divergence 0. Okay. The curl is, let's do this one. Curl of my v vector is given by this is to compute the determinant of a 3x3 matrix. The first row is I, j, k. The second one is partial x, partial y, partial z. The last one is whatever vector field you have defined. You put just I in there. Whatever value in front of x over here, this is z. Whatever in front of y is here is x. Whatever in front of k is y over here. So that, okay, so that's basically what the sequence you put over here is. You put this, the first one is I. They're corresponding to each other. Okay, so it's defined by LV. Okay, so after doing that, you just have to compute the 3 by determined by the determinant 3x3 matrix. So it's just given by I negative 1 plus 1. Okay, you follow the same thing. Okay, then I have just ignore the first row and the first column where this I vector is on. So it's first row, first column. So we delete the first row, first column. So I have partial over y, partial z, and xy, plus fj vector negative 1, this is 1 plus 2, and I did the first row and the second column is partial over partial x, partial over partial z, and this is z and y, plus k negative 1 plus 1, did the first row, last column, I have partial over partial x, partial over partial y, and z and x. So if we do the whole thing, do all the computation, what it ends up having is I times 1 plus j times 1 plus k times 1. So which means I have curl is 1, 1, 1. So curl is the same at any place, at all points, the same. So it's same rotation at different points. Okay. So this is question number 7. So question number 8. So this problem has 2 parts. So the start of the problem is if we have a scalar field defined as f, x, y, z. So this is a scalar field. This is defined as y sine x minus y, z. Okay, that's my vector field. The first question is a scalar field. Sorry. The first question is find the gradient of a scalar field. Okay, the gradient, as I mentioned before, the gradient is f is partial f x y and z over partial x I plus partial f x y and z over partial y times j plus partial f x y and z partial z times k. So that's my gradient. Okay, so when you do the partial derivative, I'm not going to ignore this part. I'm going to keep moving forward because the partial derivatives, you just consider for partial f over partial x, you consider yz to be constant and you can take a partial derivative. So the outcome for the gradient computation is y times cosine x times I and plus sine x minus z j plus it has to be minus y times k. So that's my gradient. Okay, so the second part of the question is I want to find a unit vector. So find a unit vector that points in the direction of the maximum increase as a point that points in the direction of maximum increase of the scalar field at point at pi over 2 -4 and -2. Okay, so basically you want to find a point. You basically give a point. I want to find at this point what is the direction that gives the maximum increase of the scalar field, scalar value, basically, right? Okay, as I mentioned in class, basically the gradient. So let's say the gradient. Let's say the gradient. Basically, the direction is this is a gradient for this point. The gradient is a direction of the maximum increase of my function f x y z. Okay, so basically this problem has 2 components. First one, hey, I want to compute the gradient at this point, of course. The second one is because I want to find a unit vector. So that's the gradient does not mean it's a unit vector. So let's first compute what is the gradient of f, x, y, and z when at this point, which is pi over 2, -4, and -2. Okay, fortunately, what I computed over there, which is this a gradient. So we just have to replace the x by pi over 2, y by -4, and the z by -2. So, okay, that's it. So I computed that. So this is y is -4. So -4 times cosine pi over 2i plus sine is sine pi over 2 minus z is a minus 2. So it's plus 2 j plus minus y. Minus y is positive 4 times k. Okay, so cosine pi over 2, this is just 0, it's gone. This guy is sine pi over 2 is 1 plus 2 is 3. So this is 0i plus 3j plus 4k. So that's my gradient. Of course, I have to find a unit vector, right? This is not because this is not a unit vector. So I find the unit vector. So the unit vector is determined by this gradient. You value this pi over 2, -4, -2, and then divide by the magnitude of it. They give us the unit vector of it. Positive 2, negative 4, negative 2. Okay, which means I already computed over here. This one is given by, I can write this as vector form, okay, as 0, 3, and 4. So the magnitude of this guy is the square root of each component square, right? Square root each. So 0 squared plus 3 squared plus 4 squared, okay? So this one be the same, 0, 3, and 4. So this one be square root of 0 plus 3 squared is 9, 9 plus 16 is 25. So square root of 25 is 5, so which means is 0, 3, and 4 divided by 5. Okay, you can write this one as 1 over 5 of that. Okay, 1 over 5 times 0, 3, 4. You can also say this is equal to 0, 3 divided by 5, 4 divided by 5. So that's also okay. That's the unit vector. Apparently you can check this is unit vector, okay. Okay, so we next move to the question number 9. So question number 9 is about vector integral. Okay, vector integral. So the first one is to compute a line integral. So so the first one is saying, question number 9 says, let f vector field defined by the gradient of some scalar field. Okay, well, where I have this f, the scalar field is defined by x squared times y plus y squared times x. Okay, and also I have path C, okay, which is any path from the point, which is 101 to point 2 and 2. Okay, that's a path. You can define any path. So my goal is to compute line integral of over this C. C is my path, f dot dr. Okay, this is my line integral. Okay. So the reason that I don't define this path specifically, because this is so here's an answer question. So this is a path independent problem. Okay, independence. So whenever I tell you this is vector field is given by gradient of something, a scalar field, so it's line integral CF dr is independent of the path, which means, hey, I can pick any path I want. You can pick a path, for example. You can pick, say, this is from 1 to 1, this is 1, 1, this is 2, 2, for example. Hey, I just can pick this line from here. Okay, well, I can do this. You can just pick a line and just compute the integral, which is fine. The even simpler case solution, a way to solve this one is, was the line integral of f dr is just given by fr evaluated as a point. This is the ending point minus fr and starting point. You just have to evaluate the scalar value at the ending point and minus the scalar value at the starting point. Then that's minus, you do the minus, that's the integration. Okay. You can also explain why, because it only depends on the starting point and ending point. It doesn't care. It doesn't matter which path we select. So this one, if you do that way, so because fr is s squared, it basically has s squared y plus y squared x, and you just replace x by 2, y by 2, and minus the same thing, which is x squared y squared x. You replace x by 1 and y by 1. Okay, when you do the computation, you actually get the value is equal to 14. So I just not step, just x, you do it by 2, y is 2. Okay, this is x is 1 and y is 1, and just replace the value, do this minus, you get 14. Okay. All right. So this is question number 9. Okay. The question number 10 is give a vector field given by f. This vector field is f x y, which is 2x squared I plus 2y squared j. So this is my vector field. And the passive C, okay, is given by R T is T I plus 2tj, and my T is from 0 to 2, so that's my path. So I want to compute the line integral C F dr. Okay. Now, first of all, generally in this case, if I were to give you a form of C and give you F, now you can compute it directly. Of course, you can check if it's path independent. I'm not sure if it's path independent or not, but you don't have to check it because it's not very complex. Okay, we can use a definition. We can use a standard approach. We can compute the line integral. The line integral of C over F dr is given by integration of, you just replace. So you sort of can consider this one as, I can write this one as RT is, you can say this is XT and YT, okay? Because this XT, this is what happened for the i's for the j. So because this is one is equal to Ti plus 2tj, you can see XT is T, YT is 2t, okay? So of course your f function also have x and y, so you just have to replace whatever x you hear by this value, the t, and the y by 2t, that's it. So, and your integration will move, for C you move from, because defined from t to 0 from to 2, you just say from 0 to 2, okay? Now you do f. F is, you have to replace the x by t, y by 2t, so it's, here is, and write as vector form. You can read this as 2x squared, 2y squared, okay? 2x squared is x is t, so it's 2t squared. This is a 2y squared, y is 2t, so 2 times 2t squared, okay, which the right is a 2t squared, this is 8t squared, okay? So this is 2t squared and 8t squared, okay? dr, okay, dr is r dot t and dt, okay? So give you r, so r dot t is the derivative of each component with respect to t, so, okay? The first one, this is a t, so dr over its derivative is 1. The second part is 2t, so derivative is 2. So this one is given by integration 0 to 2, 2t squared, 8t squared, dot product 1 to 2 over dt. So that's it. Now we just have to compute the product. Dot product says is the first one times first one plus second one times the second one is 2t squared plus 8t squared times 2 dt, so which is hold on a second, I think this one is 2y, okay, this one is 2y, so got something wrong over here, okay, I'm gonna have to make a change over here, so this is 2y, this is a 2 times 2t, okay. So I'm gonna have, this one is 4t, so make sure I get it consistent. So this one is 4t, and this is 4t, okay. So this one is 2t squared plus 8t over dt, okay. So this one, the integration of 2t squared is 2 over 3t cubed, plus this one is 4t squared. Evaluate at 2 and 0. Okay. So which is given by 2 over 3 times t to the cube is 2 to the cube is 2 to the cube plus 4 times 2 squared. Okay. You minus 0, basically minus 0. Okay. So this is 8 plus times 2 is 16 divided by 3 plus 4 times 4 is 16. Okay, so this is you can just leave it over here. So if you want to do this one is 16 plus 3 plus 3, 48. Okay, it's 64 over 3. That's also okay. Okay. So I'm gonna do this one stop over here as part 1, and I'm gonna go ahead and record the second one, which will cover the second part of the final exam review.